This video is based on a presentation that I gave for our Graduate Resource Center. It introduces KNIME. KNIME is a data science platform that allows you to perform data science tasks without any coding, just based on a graphical interface. If this is what you're looking for, KNIME is for you. KNIME is an alternative to R and Python for those of you who do not want to code. And the best thing, KNIME is free and can be downloaded at this link here, knime.com downloads. So the obvious question is, well, isn't Excel also low code, no code? And the answer is yes. But I strongly advise not to use Excel. Copy and paste in Excel is prone to error. If you work with like 20 records, yeah, copy and pasting is not a big deal. If you work with 520 records and you just copy and paste incorrectly, you might get totally wrong results and you might not even recognize it. Excel research is difficult or even impossible to reproduce because Excel does not leave a trail, or if so, then a very convoluted trail. All these A's, 23 plus 3 times B, 46. In contrast, R and Python, they leave a trail because you code and you save the code and you can execute the code again and you get exactly the same results. KNIME also leaves a trail. We have the workflow nodes and you can just execute them again and you get the same results. Again, Excel does not leave a trail, and that's bad because without a trail, reproducibility is not possible. And that's important for credibility. More and more journals want results that you can reproduce. They want their data. They want your code, or in the case of KNIME, they would want your workflow. And also for the future you, when you catch up on a research that you have done a year ago and you have done it in Excel, there's a good chance you do not even know what you did before. With KNIME, R, and Python, there's your trail. You can do it step by step. So what will be covered today? We will cover a basic example to compare means from 2 samples, which is very important for social sciences. Think about approaches like A/B testing or experiments where you have a treatment group and where you have a control group and you want to see which mean is higher. We will cover linear regression. That's a standard tool. And I also want to show you that you can use KNIME for more complicated tasks. In this case, a machine learning task. We will use the k-nearest neighbor model with KNIME and compare it to R to predict the wine colors of about 900 wines. So let's start. The data we are using, I use the Wooldridge dataset. That's a famous dataset. It's from 1976, so a fairly old dataset, with 526 female and male observations, including their wage, their sex, their education, and experience in years. The advantage of using a relatively old dataset is we know the result already. Of course, 1976, the salaries of females were lower than those of males, and clearly there was wage discrimination. The question is only, can we find it in the data? Here is a snapshot of the data. It just shows the wage variable, and the wages are low. Remember, they are from 1976. And we have here another variable called female. It is 1. If we have a female observation, it's 0 if we have a male observation. So let's do our research in KNIME step by step. You can later find the completed workspace at the KNIME Hub, and I will show you later a little bit about what the KNIME Hub is. Just search for compare means. Here is KNIME. Here is your workspace. And currently your workspace is empty. And of course, for every analysis, we need data. So we go here where we find all the nodes. These are these tasks. And conveniently, the Excel reader is already here. I have my data in Excel on my computer. I double click here and I adjust some settings. In this case, I want to use my local file system, and the data are in a folder on my C drive, temp on C. And here you see data, wage. These are my data. I open the data and I see already a snapshot of the Excel file. What is nice is I can transform the data here already. I can select which data I want and which data I don't want. I can rename them here. And I prefer upper camel. I prefer to call this one here sex because it shows the sex of the observation, either male or female. And as a reminder that female is coded as 1, I write sex female. I also want this variable. It shows if the observation comes from a metropolitan statistical area. So we don't want to compare rural and metropolitan data. So we will later filter the rural data out. So I call this variable here MSA yes. I say okay. And if I execute the node, see the node is not executed. It's yellow. If I execute the node here, I see already I have here my wage. I have here the sex. This is a woman. This is a woman. This is a man. And here the indicator if the person lives in a metropolitan statistical area. So what I want to filter the rows here so that I only have people who live in MSAs. And for that, there exists another node. It's called filter row. It's a row filter. I connect these two ones. That makes the data, all these black connectors, make the data flow to the next row. I double click here on the next row and I add a filter criterion. And what I want is MSA, the variable MSA should equal to 1 because that means the person lives in an MSA code. I add the criterion here. Here's the old one that I don't want. And I say, okay. And if I now execute this node, I can either do it here or here. You will see I have the similar data. I have male and female, but I have only people who living in an MSA. I filtered by row. The variable MSA, I don't need it anymore. So I can get rid of it because something like a column filter exists. And I can decide which columns I want or which ones I don't want. I double click here and see here all the selected ones, but I don't want MSA anymore because it's not needed anymore. And if I execute, you see it's gone. So now what I want is I want the average wage of the male and the female, but they're all mixed up here in my table. So I want to group them by female and by male. And then for each group, I want to calculate the mean. For this one, I have a command. It's called group by, which actually does both. It groups and aggregates at the same time. So I push the data over here, group by, I double click. And what I want to group by sex. And I can already aggregate here, see as an aggregation tab. And here I can say, I want for each group the wage. I want the mean wage. Maybe I want something else. Maybe I want in addition the median wage, or I want in addition the variance. I add these ones here. And as a result, I get here, you can see it down here, 0 are my males, 1 are my females. For these groups, you can see the mean is 7.6, so a lot higher than 4.83. If we use the median, we can say the same thing. Median is higher for male than for female. And interesting, the variance is also higher for male. I can see that this comes from males who have a very, very high wage. They work in managerial positions, and at 1976, managerial positions were practically blocked for female workers. So that makes sense too. Well, the question here is, and in statistics, we always have to answer this question. Maybe that we get this higher wage for male than for female was just an accident. So I can run a t-test. And I want to show you a nice tool here. It's AI supported. And I can ask questions. Which node runs a t-test on groups? And I shoot it off. Here's the answer. I skipped the text here. You could read it, but I know already this is a node and I just drag it here. I have to be careful. The input in this node are my data and not the results from the aggregation. So what I want to do is I want to connect the data, the filtered data, to the t-test. I want to also show you something else. This is nice to present. Maybe this data cleaning is a little bit overwhelming for your users. So what you could do is you could group these one. It's called a component. And I have it here. And I could call it data cleaning. That makes my workflow a little bit simpler. The user or you can always open the component. Then people see what's in there. Close the component. And now if I execute the component, everything that's inside there, the filter the rows and filter the columns, is executed at the same time. So whatever comes out here in terms of data goes into the independent t-test. And the t-test actually assumes that there is no difference between the two means. So the t-test would assume that men and women make the same wage. And then it calculates the probability that this assumption is correct. And the logic is if that probability is very small, we can reject the hypothesis that man and female make the same. And thus we have some evidence that the means are different. So we want to analyze wage. So we get rid of this one here. I also have to choose my groups. One group is male, one group is female. So I click it again, execute it here, and it's green. And here below you see the result. We have two results, and if we make this a little bit wider here, you can see for the first test it was assumed that the variances are the same. Probably not. We saw they were different, but we don't know for sure. For the second, it was assumed that they're different. The results are pretty similar, but still we should use the right test. And what is provided here is the so-called Levene test that has as a hypothesis that the variances are the same. And you can see here that the probability for this to happen is almost zero. So the variances are actually different. Okay. So what we actually need is only this test here. We're done. We can show here the probability for male and female wages to be equal is pretty much zero. So we have our results. We know with the very high likelihood that male and female wages were different, that female wages were smaller. I want to show you one more tool here, which are the view tools. And I show you just one here. I put it here, the table view. If I connect this here, and I connect it to the output where I find my t-tests, and if I execute it now, you can see the same results, a little bit nicer formatted. But what you also can do is you can scroll down here and you say show only selected rows, because we know that the variances are actually different. So it's enough to show that one. And now if I show it again, I can reset a node here always, and I execute it again. You see now only this node is shown here. I could connect a table view that shows the Levene test. And if I execute it here, you see the results. I could take another one here, which shows our descriptive statistics, where it shows the mean wage is 7.6 for men, but only 4.8 for women. Why would I do that? Well, it looks a little bit better, but also if you want to create a report, there are several tools, and one is very sophisticated. It's called BIRD, Business Interactive Reporting, and you can integrate these views into your report. You can add text, you can add titles, you can add images, and so on. Okay, that is our first step. So I go back to the presentation. We can actually summarize. Female wages were lower in 1976 than male wages. and that the result was most likely not derived by chance. The question is, was this wage gap created by discrimination or by a lack of female education and experience? To get the answer for that, we would have to control for education, for the years of education and experience. We have to run a regression analysis, and I want to show you how we can do that. Here's our variable of interest, and this one here, the coefficient, will later show us by how much the wage goes down if we have a female. That is actually our coefficient of interest, but we control here for experience, for the years of experience, for the education, and we have a constant here. And this is what we probably would do just out of our intuition, but research has shown that the results are more reliable if we don't use the wage, if we use the logarithm of the wage, and if we don't use experience, we use instead the squared experience. That sounds scary at first, but fortunately, the regression tool does not care which data we push towards it. So we only have to create a new variable, the logarithm of a wage, and a new variable, the square. We also will use all of the data, not only the MSA data, but we will control. We have a variable that has metropolitan statistical area, yes or no, and that will control for rural versus metropolitan. Let's do this. I go back to KNIME here. And this workflow, I don't go step by step. I have written it already. And I want to show you how easy it is to load a workflow. This workflow is not on my computer. I put it on the KNIME Hub, on the community hub, where you find a lot of workflows. And I get this one down for you here. You see here on the left side, you have KNIME. There's still our old workflow, the one we just developed. And on the right side, I have another window. It's internet browser. I connected to the KNIME Hub, and you find like 25,000 different workflows published here from the KNIME community. They develop their own components and extensions. So what we want to do, we want to search for one. I called it wage regression. It's still here. So I just search for it. And here it is. I'm still in my browser, and it has explanation and everything. I don't want to bore you with it. What is important is this symbol here. You don't have to install anything. You grab this symbol here, you drag it out of your browser, you drag it into the KNIME program, let loose, and it takes a moment, and there it is. I don't need my web browser anymore. And now instead of doing everything, I can show you the completed workflow. So first of all, we have an Excel reader tool, but there's a difference. This time we read it from the internet. See, this is the internet address. So files from the internet can be directly written into KNIME. I again look at the transformation. I have the wage, the education, the experience, sex, female, and MSA. But how do I calculate the logarithm of the wage? It's here. There is a node. It's called math formula, and I can show it to you. I just delete this here. And what I want the logarithm. Here it is, one of the functions. And I want to use the wage. That's all I have to do. I say, OK. When I execute this one, you will see I get a new variable here, the logarithmic wage, which is basically the logarithm out of this way. That's good enough. I do the same thing here to get the squared experience. And there you can even easier see it here. This person had 2 years of experience. Experience squared is 4. This person had 22 years of experience. If you square that, you get 484. So what is very common in machine learning and should be done for linear regression too is we create 2 data sets. One we use to optimize our model. That's a training data set. And one we use to evaluate the quality of our model later on. And this is one that the model never has seen before. So I do this here with this partition node. My whole data set goes in there. And here it says assign 70% of the observations randomly to the training data set and the rest to the testing data set. Training data set is up here and testing data set is down here. I execute this node here And before I use it for the linear regression, I just want to show you that I also can use plots very easily. There is a node called scatter plot. I used it here on the training data. And here is the graph. I close it because we want to do the analysis. I connected the training data here with the linear regression learner. That's my linear regression tool. I execute it. And what I get here is a table with the results for the linear regression. I push it to a table view to make it look a little nicer. And if I click here, I get the result. So how do I read the results? They are, if education changes by 1 year, then the salary goes up by 7%. That's reasonable. If sex changes from male to female, the salary goes down by 37%. And this is after I have corrected for education and for experience already. If somebody lives in a metropolitan area compared to a rural area, that increases the wage by about 12%, and all variables are significant. So the chance that this coefficient is 0 is actually 0 or almost 0. So I've created my model, and now I want to use this model to predict the testing data. And the cool thing with the testing data is they have all the independent variables, but I know the truths already. So I can compare predictions and truths and see how good my predictions are. So this blue node is not a data table. It's something else. It's basically my model. I connect it to the so-called regression predictor. I put my testing data into the regression predictor. I click, I execute it, and I have my prediction. And you find them here. Here is the predicted logarithmic wage. I like to get the real wage, so I use a math node to convert the logarithmic wage back to a real predicted wage. And now I have something, it's here's my predicted wage, 5.3. The wage was 6.25. So I can use the scorer to compare all these data and give me some metrics. They are in here. I put them to a table, so it looks a little bit better. Here are the result. My R-square on the testing data is 30%. That's pretty good for so few variables. My mean absolute error, is $1.8. So in average, I mispredicted by $1.8. That's not too bad either. Our regression is done. Okay, now we reach the last one. I want to show you how easy it is to do even more sophisticated tasks. We want to predict the color of a wine by its chemical properties. And we do it first with KNIME, and you can later download the workflow here. And then we compare it to an analysis I did in my machine learning book, and we'll see how similar the results are. They will be not exactly the same because K-nearest neighbor uses some degree of randomness, and this randomness is different, but they should be at least similar. So here are the data. We have the wine color. These are only red wines in the first records, but in the following records, we also have white wines, and we have chemical properties here. And I have to admit, if you show me these chemical properties and ask me to estimate the wine color, I have no idea. We have a total of 2,238 training observations. This is what we use to optimize the model, and we use 960 to predict. So we push these variables here to the system, and we try to predict the wine color. We know the right wine color already, so we can see if it was predicted correctly or not. So how does K-nearest neighbors works? We don't have a lot of time, but I just want to give you the idea. Let's say we have only two variables, acidity and sulfur, and I plot some of my wines here. We have a blue wine. That's the one we want to predict. We know its acidity and we know its sulfur. And we have wines from the training data set. They are either red, like here, or like white, like this one. And this is zoomed in. So what do? I look at the 4 nearest neighbors because it's k equals 4 nearest neighbor. I could use another k. If I use k equals 1, this is the nearest neighbor. It's white. I would predict this wine as white. But I will look at the 4 nearest neighbor. So I have 1 white wine and 3 red wines. And the vote is 3/1. We predict this white here as red. If we had 3 white wines, we would predict this one as white. If there is a par, the computer simply flips a coin. I hope you get the idea. That's good enough for what we do. Something else here, if we look at the scale here, these numbers are all in their 60s. These numbers all are below 6 and 7. So these numbers have way more influence than these numbers, and this is not what we want. So we have to scale these numbers into a comparable scale. Keep this on the back burner. We will do it in a moment. So we go to our KNIME demo, and I have it here. I read the training data. You saw that KNIME can generate training and testing data by themselves, but what I want to do here, I want to make sure we really work with the same data. So I created training and testing data with R and put them on the internet, and I read the training data here from the internet. They are now in a CSV file, so I use this slightly different reader. And I want almost all variables, but quality is really not relevant for a red wine or white wine. We can't say that red wines are better or white wines are better, so I exclude quality here. If I execute this, I get my data. I do the same thing for the testing data. I just read a different data set. And I told you already I have to normalize them, get them in a similar range. So I connect this one here to a normalizer. And if I double click, I can choose the type of normalization. I want z-score normalization. You might remember that from statistics. I subtract the mean and divide by the standard deviation. The only thing what is important for us, it will mostly get the data, all data in a range between negative and positive 4, maybe negative and positive 5, but not much off. So I say, okay, and click, and boom, the data are normalized. Yeah, you can see it here already. See, they are all acidity, volatility. They are all in a range somewhere between negative 4 and positive 4. So you would think I do the same thing with the testing data, but there is a problem. If I do that, I use a different standard deviation here than I have used here. And if I later compare data that were differently normalized to see how well the k-nearest neighbor works, I probably get worse results. What I want to do, I want to normalize my testing data, but I want to use the standard deviation and the mean that I got from the training data. So I get them down here, and you see this node is called normalizer apply compared to normalizer. I click, and my data are normalized. So now, remember, first I need the training data. These are the data where I find the 4K nearest neighbors. And second, for the testing data, I predict if they are red or white. And I can click, and I get the result here. Here it is. If I go all the way to the right, here's my prediction. And you can look. It's pretty good, actually, if you try to remember white, red, white, red. So the first ones are always alternating by accident. White, red, white, red. So the first six ones are predicted correctly. Question is how well I predict. And there is something, it's called a confusion matrix. And it's actually not that confusing. I just look which ones are predicted correct, which are predicted wrongly based on these 2 variables here. So if I go there, I tell the scorer the first column, the truth, is the wine color. The second color, the prediction, is in the last column that I showed you. It's called class predicted. I run this here. And here's my result. The confusion matrix is relatively easy to read. Here in this column, I have all the white wines. From the white wines, 477 are predicted as white, so they are predicted correct, and only 6 are falsely predicted as red. Let's look at the red wines. Here are all red wines. 3 of the red wines were falsely predicted as white, but 474 are predicted as red. That's an incredible good result. So the question is the result similar to what I get in R? So I go back here, go to R, and I will show you the code. I will not comment a lot on it. I load the data like before. I exclude quality. I did that in KNIME too. And this is like a math command, similar than the math node. I convert wine color as a factor. It's a special variable type that R needs, and that's it. And I print out the results here. I do the same thing for the testing data. You see the only difference is I read another file. So now I have to set up my K-nearest neighbor model. First, I need a recipe. That's basically how I deal with the data. Wine color is what I want to predict. Then comes this weird symbol. It's called a tilde. And then here I would list all the acidity and alcohol level, but I can just put a dot and say, use everything. And that's okay, because remember, quality was thrown out. Everything is done with the training data. And I normalize all my predictors. That is my recipe. It's just like an instruction now. Nothing has happened. I have to design my model. I save the designed model in this variable here. The command is nearest neighbor. I want 4 nearest neighbors. And this is one just to make sure R uses the textbook version, so it's comparable. This is the nearest neighbor is stored, and I want to do a classification. So pretty straightforward. Now it's time to putting it all together. I have a workflow, and that is actually where things happen. I add the recipe, same name that I had before, see, recipe wine. I add the model, same name that I had before, model design KKNN. And I run the whole thing with the training data. I'm done. My K-nearest neighbor model is done. Now I want to predict with it based on the testing data. This is what I do here. The prediction command is called augment. I will not go in the details why. I use the model that I just created and already trained. And I want to predict my testing data. And again, it's nice. I predict the testing data, but I know the truth already. So if I do that here, here's my result. And I get an extra column here. That is a prediction. A white wine is predicted, a red wine is predicted, a white wine. And I have the truth here too. First was right, second was, so it looks good so far. What is the confusion matrix? Well, there's an R command for that. And very similar than the node, take the data that have the prediction, tell me where I can find the truth, it's in the column wine color, and tell me where I find the prediction. The rest is done by this command, and it creates a confusion matrix, very similar to the one that KNIME did, and let's look at the results. They are almost exactly the same. Remember, KNIME predicted 6 of the red wines wrong, so does R. KNIME predicted 3 of the white wines wrong, and R predicts 2 of the white wines wrong. That doesn't mean that R is better. What this means here is both programs produce very similar results. And this is actually what we expect. So both programs worked pretty well. Thank you for coming, and I hope to see you again. If you're interested in machine learning, I recommend my new book. You find a link to an intro video for the book here on this slide. Thank you and goodbye.